So, without any further ado, up to my horrible ability to pronounce French names, and you'll probably want to say your name in a proper French accent, because I cannot do it because I have my horrible ear-scratching American accent here. But with that aside, Alba Málaga will give us a talk on 3D printing mathematical surfaces. And according to your website, you're currently working for Dynamical Systems, if that's correct. So if any of that information is wrong, please correct me. And thank you for giving us this talk today, please.
Okay. Hello to everybody. My name is Alba Málaga. What I will be talking about today is a tutorial style introduction to 3D printing one specific kind of mathematical objects, specifically mathematical surfaces. I have learned this from many people, and I will tell you when I'm talking about them. Okay. That was unexpected. Okay.
You probably just need to press R for the, yeah.
So let's go straight into the point. And as I know, there is no actually direct 3D printing access at Chennai. I will start by introducing briefly what this is all about. So 3D printing sounds like something very new to a lot of people when they don't do it yet. Actually, it's not so new. It's the patent for the most common 3D printing technique called FDM expired in 2009, and that's what made suddenly the 3D printers cheaper and cheaper. Like the price of FDM printers passed from about 10,000 euro for a decent one to 2 years later it was under the 1,000 euro for a printer. There are other 3D printing techniques that remain still expensive, but a lot of them actually have patents close to being expired, so they will probably become cheaper very soon. So how expensive is actually a 3D printing? If you want a machine that can be used immediately without too much hassle, etc., the kind of usual reference is Ultimaker. That's a few thousand euro. For the Ultimaker 2 is about 2,000. The next one will be rather around 5,000, but it remains the order of magnitude is a few thousand euro. But if you want to make it even cheaper, you can buy what we call a rewrap-like 3D printer in kit, and that will be 200, 300 euro. The one here in the example I mounted, that's not the picture of mine because I had no good enough camera, but this one is something you can build up in one day, and this way you can make it much less expensive. Nowadays, the most popular model is maybe the Creality Ender 3 in that range of prices, a few hundred euros. So how does it work? Well, you need a supply in order to be able to 3D print. And for the FDM 3D printing, the supply is this corn-based plastic, PLA, polylactic acid. The cost of one such thing for 1 kilogram, it will be between 10 euro and 30 euro for the most expensive and most high quality. For mathematical 3D printing, you need a good filament because it's often very challenging with respect to shapes and such. So how does it work? You have this plastic filament that's connected to the machine, and this plastic wire will be pulled by a tiny motor. The print head hits it And when it hits the plastic will melt. And in these cheap 3D printers, the kind of plastic that is used, the PLA, has a very low melting point. So the usual temperature of the nozzle is around 200 degrees for the 3D printing. And the bed here is around 60, 70 degrees, Celsius degrees, I mean. So this way you have this plastic being melted, and then this plastic becomes like ink. So this wire gets deposited along like 2D designs, layer by layer, and it's the superposition of these flat drawings that will make the 3D object. So typically for high quality, well, it's not so high quality, but like the higher quality objects, it will be about 10 layers per millimeter. Or if you want to do something fast, maybe it will be 5 layers per millimeter, but that's the order of magnitude. So that's the general idea of how 3D printing general object means work. But in the middle of all that, how do we get a 3D surface out of its equation? For 3D surfaces, the general method will be, first you need a mesh. So what is a mesh for a surface? A mesh is just like a triangulation or a quadrangulation of the surface. It's a discrete approximation of the surface, but by triangles or quadrilaterals. So in order to do this, you can use, for example, SageMath. You can use some other software like MathMod that I will show in action very, very quickly. Okay, and once you have the mesh, typically what will happen is that this mesh will be just the surface, but the 3D printer, what it needs is a solid. If the surface is not watertight, you will need to make sure that it encloses volume. So usually the way it's done is that it has to be thickened. So you either write your own code to make it thicker, or you thicken it using Blender, and then you export the result as an STL file, which is again a file that is keeping a lot of triangles. So for so far you have just triangles, but what happens is that the machine do not understand just triangles. The next step is what we call the slicing. So to tell the nozzle, remember, is the part that is hitting the plastic here. Okay. So the nozzle needs to know what path it will follow to make each one of the flat designs. So this kind of information is kept in what is called a G-code file. And in order to do that, you can use a slicer like Cura or ISSL. So these are like the 3 basic steps. That's what works when everything goes fine. If you need to keep in mind like 3 things in order to be able to 3D print mathematical surfaces, this is the 3 things that you should remember: mesh, solid, slice. If you are able to do those 3, you covered most of the cases, but there are still some particular stuff that needs to be discussed apart according to the cases of what you want to do. So, before diving in the actual tutorial, let's get a tour of contemporary mathematical creation, let's say. And I need to ask your comprehension, because the examples I know are, of course, influenced by my own experience. So I have worked in Europe, in the United States, and that's why in the tour there is mainly people from Europe or the United States. But if you know of anybody from elsewhere in the world doing these kind of things, please just tell me, and I will enrich my list. And so, for example, and in the handouts that I distributed to you, and that will be available on the website, you have the PDF, and each one of those links is activated, and I verified they are all working. So My first example is Silviana Ametist's work. So she's one of the developers of Bertini Real, which is a mathematical software that you can use for computing algebraic surfaces. An algebraic surface is a surface that it's defined by polynomial equations, and approximating roots of polynomial equations is something that has been known to be tricky even before the advent of computers. It's like very old theory. So even before computers, we knew that it was hard, and then, well, it's still hard. It's still an open problem to have certified computations for algebraic surface, in the sense that they very often will have these. They will very often have singular lines, singular points, and restituting those correctly is a difficult thing. Can you see my video?
We can see you, and we can see the mathematical galleries.
Okay, very good. So what is there's of course a very formal definition of what it means to be smooth or singular on some part of the surface. But when you have the 3D object, what's going on is just smooth is where you can go with your finger easily, and then when you reach kind of obstacles, that's the singular lines. So those singular lines, it's hard to get them, and the Bertini is one good solution to get good approximations for that. Here I have another example. David Bachman, who is a lecturer in the United States, and he works in a place where he has colleagues who are artists, so in the college where he teaches. So he's a very nice examples of mathematical jewelry, and in general the aesthetic approach is quite good. Kenneth Baker with some combinatorics examples. Ken Bracke, we will meet him again because he doesn't only made a lot of mathematical objects in 3D printing. He also distributes a software called Surface Evolver that allows anybody to dive in minimal surfaces. A minimal surface is a surface where there are some constraints, and under those constraints, you are looking like for the smallest possible surface. So you can have a global minimizer for that problem. It's an optimization problem, or you have just critical points in a way, like surfaces that are not necessarily minimizers, but are critical points for the problem. Those are called the minimal surfaces. And the intuitive approach to that is that those are the surfaces that you have, that you could get with bubble soap film, according to some constraints. Arnaud Cheretard is a colleague from here, from France, and has also a lot of original objects to show. Jonathan Shertock, he's an architect from the United States, who was one of the first to try to reproduce a very famous historical collection of mathematical objects that was produced in 18th or 19th century in Germany, in the Brill-Schilling workshops under the supervision of Felix Klein. So you have these very classical plaster objects that you can see in some places in the world, like Göttingen, like in France, at the Institut Henri Poincaré, or in the United States, there are a few of them in Harvard and MIT. And you have some of them in Tokyo, and I am maybe forgetting places, but the largest part of this collection is available in Göttingen. So this guy went to Göttingen, took pictures, and then started trying to reproduce them on the computer, and very soon also on rapid prototyping, namely 3D printing. He's not the only one. This collection will appear again. Francesco de Comité is a colleague from here, from France, and here we have some pictures where he collaborated with a fashion designer for designing hats on variations of cardioid ideas. This is a collective, the Geometry Werkstatt in Germany, that also does a lot of 3D modeling and 3D printing. But Sheva Grossman, she was like the precursor of all of these too. Well, nowadays she works mostly on laser engraving, but she still has a lot of models for 3D printing. George Hart, again from the United States, his website is also very rich of examples. Jeffrey Irving has some examples too. Oliver Laps is another person that worked on reproducing historical models from the Brill Schilling collection. So a lot of algebraic surfaces on his examples. Here is some artist, Luni London Tsai. Triplex is a pseudonym of a person from here, from France, who works in Toulouse and does a lot of mathematical 3D printing with some nice organic feeling to it, and whom I appreciate a lot, because actually the first time I went to a 3D printing mathematical objects workshop, it was him giving it. Here is somebody from the internet whose actual name I don't know, so I'm not sure if it's pseudonym or it's the actual name of the person. But in any case, he or she is very active in the MatMod community. MatMod was being the software that I told you about already. Saul Schleimer from Warwick. Henry Segerman from Oklahoma. He's maybe one of the most famous people nowadays in the 3D printing community, 3D printing mathematical objects community. In particular, he published a book that you can see where for some time, maybe a year, he had this exercise of trying to show everything that he could from the mathematical world with 3D printing. In the cover, the example is a demo for the stereographic projection. You have a small 3D printed object, and then you put the light on the North Pole, and then you can show what the result of the stereographic projection on the bottom. Carlos Sekin. And if you've been following, you have seen that I was following here alphabetic order. So we are very close to the end. And my last example is an amazing girl from United States, Laura Tallman. And her, the first time I heard about it was I was still just starting and being very curious about all of this. And then I saw, oh, there is somebody who decided to do one design per day for a year. The year has a lot of days, right? So she actually did it. A few years ago, she decided that she will produce a new 3D printable design, usually mathematical design, because she's a mathematician, but some of them were exceptions, like hinges or just practical stuff. And she's a very nice person, and she has plenty of examples of mathematical objects, and she shares them online. So let's dive in, and I will change now back to Firefox. Okay. So what's going on here is that there are these steps that I told you about in preparing 3D printing objects. And they can seem like simple, but actually there are some tricky parts to them. In particular, when you decide to thicken your surfaces, you can sometimes have difficult parts along very thin parts or singular lines. And this is not always so easy to solve out. So it's very nice that some people share their ready-made mathematical objects online. So, for example, here I have a small selection made by the website FunMathFun. And we can see, for example, that the Hilbert curve models by Henry Segerman are available in this website. So if there are like three things that you should remember, the three links you should remember for 3D printing, is that for mathematical objects, you have databases online, and sometimes maybe the easiest way of diving in is to find if somebody have shared them already. So in this example, we have this dragon curve example. This is a 3D object where the boundary in the bottom is what's called a dragon curve, which is a recursively defined space filling curve in R2. And well, of course, here we have it's stopped after one of the iterations. And you can just download and try it to 3D print it. The other day, one of my colleagues told me, well, the first thing I would like to 3D print is a Whitney umbrella, which is a classical algebraic surface. So the Whitney umbrella is already on Thingiverse, and what we did was just, he wanted a small one, so instead of spending too much time trying to figure this small singular line here, we just took the ready-made thing and it worked out. But of course, not every single mathematical idea have been already shared. Well, so you will still need to work if you have stuff that has not been yet shared. Another sharing platform that I would like to talk about is Imaginary. So Imaginary is an international project of mathematical communication based in Germany, but present in many places in the world. And when you go here, you have stuff that has been shared by many different people. And you, for example, here, the first image is from the Geometry Werkstatt that was also in my presentation before. The second one is from Oliver Labs. And both on Thingiverse and on Imaginary, every single shared object is under a free license. It's at least free for non-commercial use. In this example, it's for non-commercial use. A few of them are also free for like any use. So, for example, here we have an approximation of the Bartz-Sekig, which is quite a difficult surface to represent. And you want your own approximation, you can just download the files from here and try them. But what if the thing you want to represent is not here? So, this is a website that you have plenty of equations for curves and surfaces. Yeah. Of course, it's showing in French for me. Oops. English version. I'm sorry, I forgot how to access the English version, but this website has also an English version. Matcurve.com. Well, maybe I'm making a mistake, but in any case, what's important here is the mathematics. So you can still explore it in Oh, good. Here is the English version. So when you click on surfaces, you have the English version alongside, and then you have plenty of examples, and you can very quickly find some examples that are not necessarily represented in the available collections in Thingiverse and Imaginary, or that are already represented if you want to remake a model for yourself. For example, here you have the Whitney umbrella, and then you wonder, well, how do I get a Whitney umbrella? One way of doing it is to take the Cartesian parametrization and use it for making the mesh. So let's go into the example of how do you do the mesh. So this part is something that is actually possible to make with SageMath. But I like using this software MathMod because it's quite satisfying to be able to see the feedback immediately. You can do this kind of things with an Interact on Sage, but it's a little bit slower. So it comes with a lot of examples already loaded in. So let's take a simple example. So this is a parameterized apple, for example. What if I want to 3D print it? I have one problem is that it's not watertight. I have a little hole here that if you imagine it filled with water, the water could escape through here. And another little hole here. So for this one, what I would need to do would be to export the triangulation. So for that, you use the export menu of G, and then use Blender to close the holes.
Yes, Alba?
Here I have another example, the voice surface, where the difficulties will be kind of different, but all of these are like a lot of possible inspirations for you to dive in and do some mathematical surfaces. And just because, well, I'm sorry that I started so late. So the last examples I will show you here directly. So the three kind of surfaces that I like representing the most are these kinds.
Also, since we started late, feel free to take a few extra minutes too.
Thanks, it's nice, but I don't want to make you late on everything. So,
well, all we have is a coffee break after this, and you're not here, so you know there might be an angry mob, but it's my problem, not yours. So feel free to take some extra time.
So one kind of surfaces that I've been representing lately a lot is constant negative curvature. Constant negative curvature surfaces allows you to have pieces of hyperbolic plane in R3. R3 being the Euclidean space. So we assume that that's the most ideal approximation to the space that we live in. I hope there are not too many theoretical physicists in the room who will protest against that. And for me, I'm living in the Euclidean 3D space, and what I'm looking for are embeddings of parts of the hyperbolic plane into R3. Why parts? There is a classical theorem by Hilbert that tells you that you cannot put everything on it. And why do I want to make such big pieces? So it's not a big piece from the hyperbolic plane, because there is this theorem that tells you you cannot put too much of it into R3 smoothly. But physically, it's a large one. We see it's like almost the size of my head. And the reason I wanted to do this is that with a couple of friends, we were looking into the problem of creating hyperbolic paper. This website, ism.brown.edu, is summing up some mathematics illustration projects from a special semester on mathematics illustration at the ICER. And so one of the things we did was trying to do this hyperbolic paper. it's very funny because when you have hyperbolic paper, you can have things like, for example, a regular pentagon with only right angles, and then modify classical origami stuff to make, for example, the classical bird from the Japanese origami with 2 heads instead of 1. And in order to model such paper, you need large objects. So that's one a piece of a pseudosphere that was made by Aaron and Stepan. And then this short video is showing how being constant negative curvature actually means if you model paper on it, it will fit perfectly anywhere you want. And you can either model your paper on the pseudosphere or model your paper in the Dini surface. The name of this red surface is called is the Dini surface, and it will just perfectly fit back. And the Dini and the pseudosphere are already available on the library of from Sage. So that's my motivation for hyperbolic, and also that they appear quite naturally. So like lately I've been working on flat tori, and the modular space of flat tori has naturally a constant negative curvature on it. It has a geometric structure which is a quotient of the hyperbolic plane. So here I have one fundamental domain for that, 3D printed, and then I can go to my talks and just say, well, what we showed is just every point of the modular space can be reached, and just give this around the room. The other kind of surface, algebraic surface, what I like about it is the challenge. When I started this problem, I thought I didn't realize how much of a challenge it was, but actually nowadays I work in a research team where part of the team, their main job is to look for better and better ways of approximating meshes for algebraic surfaces. And the minimal surfaces is also a very nice thing to be able to 3D print them, because the definition of a minimal surface is that you need to be a critical point for some optimization problem. So usually you explain that to the general public saying that you will be putting a swap bubble film and then looking at what kind of surface does it give to you. But your critical points, where they can be stable or unstable, or they could even be saddle points. So there are some theoretical swap bubble surfaces, minimal surfaces, that are just very, very, very hard to get with actual swap bubbles. So it's very nice to have 3D printed examples. So in this example, it's constrained to have the border to be the union of a circle and a trefoil knot. If anybody of you is able to actually reproduce that with actual swap bubble film, I want to see the picture, because that's an example where in theory you can get it, but it's so unstable with swap bubble that the only way to actually touch it, or to actually have it physical, is to make it as an object. And I will stop here, and I'm here for all the questions. Thank you very much for your attention.
Let's thank our speaker. Any questions? Well, can't join on Zoom. Join on Zoom. Yeah. Well, he's setting up because he's wanting to share a screen and show something. Any other questions? I have one. Since the trefoil knot, I think of that as the Seifert surface. How easy is it to 3D print other Seifert surfaces, like say for the figure 8 knot?
Same kind of project would be preparing the 3D model wouldn't be difficult. When you go to the website and look at this particular object from Triplex, he did very detailed comments on how he made the surface.
Because it looks at least in
so you can
principle
follow
like
this and just replace the trefoil knot with the figure 8 knot. Wait, I'm looking for where the comments are. Think details. Okay, here.
Yeah, because looking at the picture, it looks like he just followed the Seifert algorithm for generating the surface of just putting little twists and connecting two discs.
By just following instructions. But it minimal or just any Seifert surface?
Well, I was thinking just any Seifert surface, not necessarily making it minimal, but I'm definitely happy to make it a minimal surface. My differential geometry side gets happy about that.
Yeah. So what I would suggest is to go to Thingiverse, look at this particular thing. The name is trefoil knot, and then follow the instructions. So Surface Evolver is available. Surface Evolver is the software that allows you to easily make these minimal surfaces. The minimal surfaces are an answer to a minimization problem. So the usual way of working with this is with a kind of gradient descent, but you don't need to know all the technical details. So you can just download Surface Evolver and then use it.
All right. Thank you.
And this has detailed instructions and a lot of examples that you can work through, and then just replace it with the corresponding variation from here.
All right, thank you. Can you stop sharing your screen for a second for our next question?
Yes. Okay, very good. So here is somebody who already exported the Klein bottle and put it into Blender.
Yeah, so I was trying to render a Klein bottle here, but the problem is when I try to shade it out, since the normals are inconsistent, I don't get a proper shading. So in contrast, if I try adding a cube, maybe the shading is somewhat perfect because I don't have a light here.
The Klein bottle is non-orientable, so effectively it's just not possible to make.
Wanted to ask if there was a workaround to at least get somewhat closer to the actual shading of a Klein bottle in Blender. I tried recalculating the normals. I tried adding a solidifying modifier as well. Sure, if you can see it.
So what I would suggest here is to do a self-intersect of the of this mesh.
Okay.
So for those less familiar with the Klein bottle is a very classical example of a non-orientable surface. And because it's not non-orientable, any embedding of the well, this is not an embedding, sorry, it's an immersion, but any realization of the Klein bottle in R3, well, it will not be possible to assign to it normals along the whole surfaces in a consistent way. And this object it's a very interesting example. Can you rotate it a little bit so people can see what's going on there?
Oh, sorry.
So it's like a bottle, but the higher part of the bottle is kind of going inside. So for 3D printing, what you would need to do is to just use the surface of it, and effectively the consistent normals. I think I forgot to speak about it, but it's important for 3D printing too.
Great.
Did I answer your question?
Yes. Thank you. Thanks a lot.
All right. Do we have any more questions? If not, let's thank Alba again.
Maybe I should just show in one example how do you thicken the surface. So I'll just take this very simple example of a parametric surface, which is called snail in math mode. You export it as a triangulation. So this is one that is simple enough to do not pose any of the problems that I thought could possibly occur. And then you open it in Blender. Blender is the software that was on the shared screen a moment ago. And in Blender, you have an operator that's called solidify, a modifier. Okay, I have the colored thing. Okay, good. How did I export it? Oh, in the root. Okay. Snail. I'll put it in my messy downloads folder. Okay. And then in Blender, I go to downloads and just take this. And this thing, if it will have normals to one side and not the other, and then what you need to do is just click on this small tool symbol, add modifier, and then you have here solidify, and then you adjust how thick you want it, and this adds the thickness that you need to for 3D printing. And then I'll stop you. There are no other questions.
All right. So there are no more questions. Let's thank Alba again.
Thank you.